In this video, we are going to learn several ways to create components in sim mechanics. Specifically, we will talk about how to define simple geometries, extruded and revolved solids, and compound bodies. The components of a simplified suspension system is used to explain the various ways we can create bodies for multi-body modeling using sim mechanics. We will model the components of a suspension system that consists of a simplified chassis, suspension arms, and a tire with rim to form the wheel system. We will only build these various components in this video. In subsequent videos, we will create a mechanical assembly out of these components by specifying degrees of freedom, extend the model by adding shock absorbers, and implement external force tests. We will start by creating the simplified chassis and then move on to the other components. Let's switch to MATLAB to see how we can do this. Let's open up a new sim mechanics template model by using the command smnew. This opens up our sim mechanics library here. Let's go ahead and close this because we are going to access this from the Simulink library. And it also opens up a new Simulink model with several useful sim mechanics blocks that we discussed in the Introduction to Multibody Simulation video. In this model, let's delete the converter blocks and the scope block, and also delete the rigid transform block because we are not going to be using these blocks. Recall that in sim mechanics, we will use the solid block to create the rigid body components. Recall also that you can find the solid block under the body elements library in sim mechanics. To create the simplified chassis, let's double-click the solid block to access its parameters. Each rigid body is characterized by a set of physical properties, the first of which are geometric properties. This controls the shape and the size of the body. The shape parameter includes several options: cylinder, brick, regular extrusion, etc. Let's change this from a brick to a cylinder. Now we can refresh the visualization by pressing on this button here or pressing the keyboard key F5. We can fit this model into view by clicking on this button here. We can also see that this cylinder can be parameterized by the radius and length parameters. Similarly, we can choose other shapes which are controlled by other parameters as well. For the simplified chassis, we will create a brick solid with MATLAB variables that specifies its dimensions. To see what these variables are, let's switch to MATLAB. Let's open up the MATLAB script file, Suspension Systems Parameters. All the dimensions required for the suspension system are specified here. For example, we see the chassis dimensions here. Let's create these variables in MATLAB by clicking on the Run button here. And let's go back to our model. And in our solid block, let's specify the dimensions as the MATLAB variables: chassis length, chassis width, and chassis height in the 3 dimensions. And let's specify the units to be in centimeters. And we can update the visualization by clicking on this button here and fit the model to view by clicking on this button here. Next, we will specify inertial properties. Let's access these parameters. This controls the mass, density, moments and products of inertia, and the location of the center of mass. By default, sim mechanics automatically calculates the inertia from geometry and density or mass. We can also specify custom inertia properties by setting extra parameters such as center of mass, moments of inertia, and products of inertia. For our example, we will stick to calculating this from geometry and specify the density to be 8000, which is the density of steel. Next, we will specify the graphical properties. This controls the color and visual representation when visualizing in the Mechanics Explorer. We could either display the shape from a geometry or as a marker. For our example, we will display it as per the geometry. Under Visual Properties, we can change the color of the displayed solid. In this case, let's display a lighter shade of red. We can also control the opacity. So in this case, let's set the opacity to 25%. We can see the updated visual representation. Under Graphic Properties, we can also set it to Advanced and control many other parameters. Please refer to the documentation to get more information about this. For our example, we will stick to using simple visual properties. This gives us an overview about the solid block and its various properties. Let's select OK to save changes. Rename the solid block to Chassis Simplified and connect the reference frame of this solid to the world frame. Recall that for the bodies created within SimMechanics, for example, the Chassis Simplified here, the reference frame is by default at the center of the geometry. Let's go back to the presentation for a bit. We saw how to create bodies of simple geometry using existing shape options such as cylinder, brick, etc. We use this to create a simplified chassis. Next, we will create the suspension arm. We can already see that this is a more complex part than the simplified chassis. None of the built-in shape options will work for this. So we need another way to specify the geometry. The solid block also enables us to specify geometries by setting its shape parameter to general extrusion. By this, we can specify the cross-section for the extrusion as an array of coordinate pairs. This cross-section is swept along the z-axis of the reference frame by a length that is specified by the extrusion length parameter. We can extrude shapes that represent the suspension arm in our case. Let's switch to MATLAB to see how we can do this. In our model, let's drag in another solid block from the Simulink library browser. Double-click the block to bring up its parameters. Let's set the shape to general extrusion. To create an extruded solid, we can specify an array of coordinate pairs here. This will extend the custom cross-section through the z-axis and the centroid located at the block reference frame. Let's take a look at a simpler example of a cross-section first that isn't in our suspension system. Let's switch to MATLAB. Load the cross-sections.mat file. This creates the t-beam variable that we can see here. Double-click the variable to access its value. Each row of the array represents a different coordinate pair. Adjacent coordinate pairs are connected with a straight line to form a closed polygon. We can visualize this cross-section by plotting the columns of this variable against each other. To do this, let's go back to the MATLAB command prompt and specify our plot command using the t-beam variable and plot the columns against each other. Here we can see the cross-section of the t-beam variable. This variable defines a constant cross-section in the xy plane. Let's specify this variable in the solid block and see what this looks like. So let's go back to our model and access the solid block's parameters. And for the cross-section, let's specify the t-beam variable as the value. Let's set this to centimeters as units. Let's also set our length to be 1 centimeter and update the visualization to take a look at the t-beam that has been formed here using our cross-section variable. Now, let's create the suspension arm by specifying its cross-section in the xy plane. To do this, we first need the cross-section coordinate pairs variable. We will generate this using a utility MATLAB function. Let's switch to MATLAB. The function we are going to use is this function. Let's take a look at this by double-clicking on this function. Note that it takes 4 parameters as inputs. This function returns the dimensions for our suspension arm. This is to illustrate that we could write our own function similarly for a shape of our choice. Let's go back to the command window and create our variable here. So suspension arm equals, let's call our function with the parameters arm1's length, width, radius, and the number of holes. Let's execute this. We can see the suspension arm variable created here. Similar to before, we can visualize the cross-section by plotting the columns of this variable against each other. So we can say plot suspension arm and plot the column 1 against 2. Let's execute this command and pull up our figure 1 here. Here we see the length of the rod and also the 2 holes. Let's specify this cross-section in the solid block and see what this looks like. To do this, let's go back to the command prompt and copy the function call here with our parameters using our shortcut Control-C. Go back to our model, double-click the solid block to access its parameters. With the shape set to general extrusion, let's paste our command here using the shortcut Control-V. So note here that we can directly use function calls for the cross-section parameter. And let's set the length to the variable arm1 underscore extrusion length. And let's update the visualization to take a look at this. Let's fit this model into view. Here we can see the suspension arm. This way, we can create more complex parts using general extrusion shape. Recall that we have the option to specify the inertia and graphic properties as well. So here for the suspension arm, let's calculate the inertia from geometry and specify the density to be that of steel, so 8,000 kilograms per meter cube. Let's also specify the graphical properties and change the color of the suspension arm to something blue. Select OK and update the visualization to take a look at the suspension arm. Now we have specified all the properties for the suspension arm, so select OK to save changes. Rename the solid block to arm and connect the reference frame of the arm to the chassis. Now we have created 2 components, the simplified chassis and the suspension arm. Next, we need to create the wheel system. Before this, let's get back to the presentation for a bit. We just saw how to create solids using general extrusion. We specified an array of coordinates for this. Note that for the cross-section parameter to be valid, the array of coordinates must adhere to the following rules. Coordinates must define a closed polygon that does not self-intersect. Counterclockwise loop encloses the solid section. Clockwise loop encloses hollow section. We used this mechanism to create the suspension arm, which was a link with 2 holes. We also saw how we can use MATLAB functions to return the cross-section of the body to be extruded. Next, we will focus on the wheel rim part. We will use this as an example to see revolved bodies. To create a revolved body, we will specify an array of coordinate pairs as the cross-section parameter in the solid block dialog box, similar to the general extrusion that we just saw. The revolution axis is the z-axis of the reference frame through the centroid of the cross-section. Let's switch to MATLAB to see how we can do this. In our model, let's drag in another solid block. This one's going to be our rim. Double-click the block to bring up its parameters. And let's set the shape to revolution. To create a revolved solid, specify an array of coordinate pairs as the cross-section parameter in the solid block dialog box. Similar to our extrusion example, let's take a look at a simpler example first that is not used in the suspension system. Let's go back to MATLAB. In our workspace, the cone variable here can be used to create a revolved body of a cone. Similar to the extrusion cross-section, we can plot the columns of the cone variable against each other to visualize the cross-section. Let's bring up the figure here. This defines a constant cross-section in the XZ plane. The cross-section is rotated about the Z-axis to create the revolved solid. Let's go back to our model and see what this cone will look like. So in our solid block, let's set the cross-section variable to cone and set the units to centimeters and update our visualization to take a look at our cone here. So here we can see the revolved body. Note that the default value for the extent of revolution is full, but we can create partially revolved solids by setting this parameter to custom and setting a revolution angle. So in this case, if we set it to 180 degrees and update the visualization, we see half of that cone. Let's use this approach to create the rim component of our suspension system. So let's go back to MATLAB. The cross-section of the rim component is specified in the rim rev variable here. This variable is defined in the script. Let's go ahead and plot the columns of the rim revolution variable against each other to take a look at this cross-section. So let's bring up the figure here. So now here is the Z-axis, and we will revolve this cross-section about the Z-axis to create the revolved solid. To do this, let's go back to our model. So in our solid block, let's specify the cross-section to be the rim revolution variable. And let's set the extent of revolution to full and update our visualization to see our rim here. For this component, let's set the inertia parameters. Let's suppose the rim is made of aluminum, so the density is going to be set to 2800 kilogram per meter cube. Let's also update the color for this component. Select OK and update the visualization to take a look at this. And select OK to save the changes for this particular solid. Let's rename the solid to rim and connect it to the arm here. So now we have created the simplified chassis, the suspension arm, and the wheel rim. To complete the wheel system, we need to create the tire. To do this, let's copy the rim part by right-clicking and dragging on this block. Rename this to tire. Double-click the block to access its parameters. We will stick to using the revolution approach. Instead of the rim revolution variable, we will use the wheel revolution variable that is also defined in our MATLAB script. Update the visualization to take a look at this. Now let's set the inertia properties. So in this case, we want the density to resemble rubber. So we are going to set it to 1200. Let's also update the color. So in this case, let's update it to dark gray and select OK and update the visualization to take a look at this. Select OK to save changes to this component and connect the tire to the rim. Here, the rim plus the tire forms the wheel system. Multiple elementary solid blocks like this can be attached to each other to create more complex bodies. Let's update this model by using our shortcut Ctrl D to bring up the Mechanics Explorer. Let's switch to the isometric view. We see that all the components are aligned along the center of mass. This is because we still need to position these components appropriately. We will use rigid transform blocks to do this. Also, when we simulate this model, we don't see any dynamics here. This is because we need to specify appropriate degrees of freedom between the components so that they can move with respect to each other. We will do this using joint blocks. We have already introduced the rigid transform block and joint blocks in the Introduction to Multibody Simulation video. We will explore these in detail in the next two videos, that is, Building Mechanical Assemblies Parts 1 and 2. For now, we have just created all the components for our mechanical assembly, and they are rigidly connected to each other to form a single compound body with a single center of mass. Let's go back to the presentation and do a small recap. We just saw how to create revolved solids. We started with the cone example. Note that the array of coordinates for revolution must adhere to the same rules as extrusion. The revolution axis is the z-axis of the reference frame. We created the wheel rim part using this mechanism. The cross-section is shown here. We also discussed that a rigid body can contain one or more solid blocks. Rigid bodies that contain multiple solid blocks are called compound rigid bodies. In a compound rigid body, each solid block represents an elementary solid segment. Multiple solid segments can connect through frames to form a single rigid body. For example, consider the rim and the tire to form the wheel system. This can be partitioned into two primitive bodies, that is, one rim part and one tire part. By affixing each of these bodies to one another to particular locations, we can create a detailed geometry that represents more complex systems. In summary, we talked about defining simple geometries, where we used the simplified chassis as an example, extruded and revolved solids, for which we use the suspension arm and the rim as examples respectively. And for creating compound bodies, we use the rim and the tire to form the wheel system as the example. At the end of this, we saw all the components lined up along the center of mass, creating one single compound body. We will talk about how to position these components, specify degrees of freedom, etc. to make this a working assembly in the next two videos, Building Mechanical Assemblies Parts 1 and 2. This concludes this video.